Hello everyone. In this video, we're going to talk about and solve some optimization problems. Here are the strategies for solving optimization problems. First step is to draw a picture if it's applicable and identify the known and unknown quantities. Then you want to write an equation, which is your model, to be optimized. What you want to try to do is then write that equation in terms of a single variable. Determine the desired max and min values of your model using calculus techniques, right? We have the first derivative test, second derivative test, etc. And then determine the domain, find the endpoints basically of your model and check if those endpoints also correspond to a max or min. Okay, so let's look at some specific examples. Example one, what point on the graph y equals square root of x, pictured here on the right, is closest to this point 5, 0. So we want whatever point here is closest to that point there. In other words, what we want to do is we want to try to minimize the distance. So we're going to minimize the distance. So we're basically minimizing the distance between 2 points. The first point, of course, is 5, 0. And the second point, which we want to try to find out, is some x value, and the corresponding y value is the square root of x. So we'll call that distance d, and that's going to be the square root of x minus 5 squared plus y, the square root of x, minus 0 squared. What we want to do is minimize d. Now, it's equivalent to go ahead and square this and get rid of that square root, x minus 5 squared plus, in this case, the square root of x squared is just x. And if we minimize d squared, we'll also minimize d. The advantage of minimizing d squared is that we don't have the square root to deal with. So let me kind of rename that. We'll call that dsq. And that's going to be, we can go ahead and multiply this out. That's going to be x squared minus 10x plus x, so it would be minus 9x plus 25. So by minimizing this parabola, I can find the minimum distance here between these, find the point that is closest to 5, 0, minimize that distance. Okay, so we'll go ahead and use our calculus techniques. We have our equation. Our equation is in terms of a single variable. We'll go ahead and find the derivative, d squared prime. That's going to be 2x minus 9. And then we'll find the critical points by setting that equal to 0. We add 9 divided by 2. We get x equals 9 halves. And then the y, the corresponding y, is equal to the square root of 9 halves, which is 3 over the square root of 2. And so our point is 9 halves square root, 9 halves 3 over the square root of 2. And that is the closest point. You could have also solved this without squaring the distance. You would have come up with the same result. For the second problem, Mr. Kelly needs to make an open top box to store all his magic cards. He has a piece of cardboard that is 14 by 30. So we'll go ahead and draw a picture. 14 by 30 inches. So this is 30 inches and this is 14 inches. So to make his open top box, Mr. Kelly cuts out squares of equal size from the corners. So he's going to cut these corners out. They'll be an equal size. And then you can just fold each of these sides upward to form his box. What size should the squares be in order to create a box with the largest possible volume? Okay, so what we'll do is we'll label this x, this little distance here. And since this is a square, it has a width of x and a length of x. Okay, so what we need to do then is we'll first find the volume. So the volume here is the length times the width times the height. Okay, so there are too many variables here we need to get rid of. We need to get all these down into terms of one variable, that x. So let's look at the length. The length of the box, once we fold these corners up, is going to be this 30 inches minus 2x. So that's 30 minus 2x. The width is going to be the 14 inches minus 2x, right? This will be the length in here of the box once we fold it up, and this will be the width. And then, of course, the height is just going to be equal to, when we fold that up, it'll just be that x, right? So now we can put all that together and get our volume in terms of a single variable x. We have 30 minus 2x times 14 minus 2x times x. And we can go ahead and multiply that out. We'll FOIL this and then we'll multiply the x. So 30 times 14 is 420. We have a minus 28x minus 60x. So that gives us a minus 88x. And then we have plus 4x squared. And then, of course, we have to multiply that all by x. I'm going to go ahead and rearrange this. So we have the leading coefficient up front. This will be 4x cubed minus 88x squared plus 420x. This is now our model. This is what we want to optimize. So we'll go ahead and use calculus. We'll take v prime, the derivative of v with respect to x. That'll be 12x squared minus 176, right? 2 times 88, x plus 420. Okay, so let's go ahead and just plot this in Desmos. I've got a Desmos window here. I'll go ahead and plot 3x squared. I don't care about the 4 out in front here. I can just divide both sides by 4, and 0 divided by 4 is 0. So I'll just go ahead and plot 3x squared minus 44x plus 105. And then we can just pick out the zeros here. We see there's one here at x equals 3, and another one here at x equals 11.667. So let's go ahead and write those down. We get x equals 3 and 11.667. This would be inches and inches. Now, looking at the original picture, we see that the 11.667 inches is not a suitable answer because obviously we can't cut that off of both sides, at least for this 14-inch side. So we'll throw that answer out. And x equals 3 inches, so the square size is 3 inches by 3 inches. And that's our answer. Okay, finally our last problem. 2 towers are 30 feet apart. We'll go ahead and start to sketch this. We have a tower here, a tower here. This is 30 feet. One of the towers is 12 feet high. I'll go ahead and draw that. That's 12 feet. And the other is 28 feet high, so a little more than twice as high. It's 28 feet. There's a stake in the ground between the 2 towers. Somewhere in here, there's a stake. The top of each tower has a wire tied to it that connects to the stake in the ground. So a wire down here like this, and a wire up here like this. Question is, where should the stake be placed to use the least amount of wire? Well, let's go ahead and define some variables. We want to know where the stake is placed. So I'm just going to call this distance between the stake and the short tower x. Of course, what that means is that the distance between the stake and the big tower is going to be 30 minus x. So what we want to do is we want to use the least amount of wire. So we need to find the total length of the wire. The way we're going to do that is we're going to use the Pythagorean Theorem. Okay, so let's call this distance, I'll call this distance A for now, and this distance B. And so what I know is that A is going to be equal to the square root of 12 squared plus x squared. That's a Pythagorean theorem. And B is going to be the square root of 28 squared plus 30 minus x squared. All right, and so I want to minimize the amount of wire, and so the length of the wire, I'll say L, is going to be equal to, of course, a plus b, which is going to equal then the square root of, I'll go ahead and multiply this out, 144 plus x squared, plus here, I need to find 28 squared is 784. I can go ahead and, yeah, I'm not sure I want to, I'll just leave that as 30 minus x squared. We don't need to FOIL that out yet. So now I have my model, I have my length, the total length of wire, in terms of a single variable x. So now I can use calculus and I'll find L prime. Okay, so this one's a little bit trickier. I have these two terms and I'm going to use a chain rule for each one. So this is going to give me 1/2 times 144 plus x squared to the negative 1/2. And then I have to multiply by the derivative of the inside. Well, that's going to be 2x. And then here I'm going to have 1/2 times 784 plus 30 minus x squared to the negative 1/2. And then I'll multiply by the derivative of the inside, which is going to be 2 times 30 minus x times negative 1. All right, so let's go ahead and simplify this. The 2's will cancel here. This will give me an x divided by the square root of 144 plus x squared. That's kind of, let me fix that. Plus x squared, plus over here, I can cancel the 2's. I'm actually going to have a negative sign come out here, but I'll just go ahead and multiply the negative 1. I'll distribute that into the 30 minus x. So I'll have a plus x minus 30 over the square root of 784 plus 30 minus x squared, like that. Okay, so we want to know when this is equal to 0. This is a tricky one to try to simplify by hand, so we'll again go ahead and use Desmos. Have a Desmos, bring my Desmos back up, and now we'll just go ahead and plot this. So I'll have x divided by the square root of 144 plus x squared, plus x minus 30 divided by the square root 784 plus 30 minus x squared. And now I just need to go ahead and find the zeros. Let's look at the graph. And it looks like there's actually a zero here right at x equals 9. So that means the answer here is x equals 9 feet. When the stake is 9 feet away from the short tower, which means that it's 21 feet away from the longer tower, I will minimize the amount of wire that I need. And that's my final answer.